Hey, welcome. Sometimes it feels like chemistry is just a load of random reactions, right? Well, today we're going to crack the code. We're diving into quantitative chemistry, which is basically the rule book chemists use to solve puzzles with mass. This is all focused on what you'll need for your GCSEs, and we're going to start with a puzzle you've definitely thought about before.
So let's kick things off with that puzzle. Picture it. You've got a big, heavy log in a fireplace. It burns for hours, and what's left? Just a tiny, light pile of ash. It really feels like something has just vanished. Poof, gone. So where did all that stuff, all that mass, actually go?
The answer to our burning log puzzle? Well, it all comes down to one single, super important rule in this part of chemistry. It's an unbreakable law. It governs every single chemical reaction there is, no exceptions. It's called the law of conservation of mass.
And this definition? This is gold. It's lifted straight from the AQA exam specification, which means you need to know it. No atoms are lost or made, so the mass of the products equals the mass of the reactants. Basically, in chemistry, you can't just create stuff out of thin air, and you can't make it disappear into nothing.
The best way to get your head around this is to think about Lego bricks. Seriously, imagine you have a pile of Legos and you weigh them. Then you build something totally different. You turn a house into a car. It looks completely different, right? But you still have the exact same number of bricks you started with. So the mass is exactly the same. Atoms in a reaction, they work just like that.
Okay, so if atoms are just being shuffled around, how on earth do chemists keep track of them? It's not like you can see them. Well, they use a special kind of accounting to make sure the law is being followed every single time. And that's where balanced symbol equations come in. Think of them as the official account books for a chemical reaction. They're the proof. They show exactly where every single atom starts and where every single atom ends up. If an equation is balanced, it's a guarantee you've obeyed the law of conservation of mass.
Reading these account books is actually pretty simple. It's just a counting game. The big number you see in front of a chemical formula, that's your multiplier. It applies to the whole formula after it. The little number, the subscript, that only applies to the atom it's sitting next to. If the atom count for each element is the same on both sides of the arrow, boom, your books are balanced.
Right, so we can count atoms. That's a great start. But what about their mass? For that, we need another tool. It's called the relative formula mass, or just MR for short. This is how we start putting actual numbers into our chemical accounts.
So the official definition for relative formula mass is just the sum of the masses of all the atoms in a formula. It's that simple. To find the mass of an individual atom, that's its Ra value, you just look it up on the periodic table. And remember, you'll always have a periodic table in your exam.
Let's do a quick one for water, H2O. First thing you do, find hydrogen and oxygen on the periodic table. You'll see their relative atomic masses. There are 1 and 16. Okay, step 2. Multiply by how many atoms you have. The formula has 2 hydrogens, so that's 1 times 2, which is 2. And it's got 1 oxygen, so that's 16 times 1. Finally, just add them up. 2 plus 16 gives us an MR of 18. Easy.
And here's the magic bit. This is where it all comes together. If you calculate the total MR for everything on the left side of a balanced equation, all the reactants, it will always equal the total MR of everything on the right side, all the products. This right here is the law of conservation of mass, but proven with numbers.
Okay, let's pause. If mass is always conserved, what about our burning log? And what about those experiments in the lab where you put something on a balance, do a reaction, and the mass clearly goes up or down? So does that mean the law is wrong? Absolutely not. It just means we're looking at the case of the missing mass.
Pay attention here because this is a classic exam question. It's literally designed to trip you up. If mass can't be lost or made, why does it sometimes seem to change? The most important word there is seem.
Here's the deal. The scales you use in a lab are only measuring the solids and liquids in your container. They're not measuring any gases floating around. So the mass seems to go up when one of your reactants is a gas from the air, like when a metal reacts with oxygen. That oxygen has mass, and it's being added to the metal. On the flip side, mass seems to go down when one of your products is a gas that just floats away, like carbon dioxide. The mass isn't gone, it just escaped from the scales. So what's the secret? It's the gas. The law of conservation of mass is always true for the entire reaction. But if your experiment is in an open system, like a beaker or a bonfire, then gases can get in or out. The atoms aren't destroyed, they're just floating around in the air unweighed.
If you did the reaction in a perfectly sealed, closed system, the mass you measure would stay exactly the same.
Okay, so that's the theory. But let's get real for a second and talk about what actually happens in the lab. Because even if you have a perfectly closed system, things are never quite as neat as they look in a textbook. We have to talk about uncertainty. You know, on paper, everything is perfect. Our calculations are exact. But the lab? Well, the lab is the real world. And in the real world, every single measurement you take, from a balance to a burette, has a tiny margin of error. No reading is ever 100% perfect. Understanding this is a huge part of working scientifically.
And this isn't just a side note. It's so important that the specification says it outright. Whenever a measurement is made, there is always some uncertainty about the result obtained. You have to accept that every measurement has this little bit of wiggle room. So, what does this mean for you in an exam? Well, the spec actually gives you a pretty simple way to handle it. If you've got a set of results from repeating an experiment, first you calculate the mean, the average. Then you can estimate the uncertainty just by looking at the range of your results around that average. It's a really straightforward way to show the examiner you get that real-world measurements aren't perfect.
So let's circle all the way back to our burning log. The mass didn't vanish, did it? It was just rearranged into invisible gases, carbon dioxide and water vapor, which floated away. The total mass of the ash plus those gases is exactly the same as the original log and the oxygen it used from the air. You now know the unbreakable rule. You know how to track the atoms in the mass. The only question is, how are you going to use it to solve the next chemical puzzle you come across?